All right, today we're going to talk about section 10.5, which is about tangents. First of all, tangent that we talk about in chapter 10 about a circle is related to the tangent that we talked about in chapter 7 with sine, cosine, and tangent. But for our purposes, we don't really need to talk about how they're related. It's kind of a crazy relationship that we don't really need to get into. So you can know that they do have the same name for a reason, but we don't need to know what that reason is right now. So we can see here that definition 10.13, the definition of a tangent, is a line that intersects a circle in exactly one point. And definition 10.14, the point of tangency, is a point where a tangent line intersects a circle. So on the right here you can see we have our circle, complete with its center point here. And here is an example of a tangent line and the point of tangency. Now what's very important for us to understand here is that this line intersects my circle in exactly, can't even underline very well on this thing, but in exactly one point. So even though over here it looks like maybe this line touches the circle on this whole little segment here, we know that that's just because of the thickness of the drawing. Really, it's only touching it at this sort of one precise point here, which we'll make a little bit bold for us there. And that's the only point where the line touches the circle, and that's the point of tangency. And the tangent line never goes inside the circle at all. It just touches the circle one time there. And then here, theorem 10.9 says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So let's look over here at our example on the right. We have our tangent line to my circle. So if I were to draw a radius to my point of tangency, which will do my best to go from the center to my point of tangency, which that was pretty good for me. Now that should be perpendicular to the tangent line. So we'll draw our little right angle symbol there. And that's okay. So this radius has to be perpendicular to the tangent at the point of tangency. Let's look down here at an example of using these definitions and theorems. So it says segment RS is tangent to circle Q at point R, and we're supposed to find Y. The first thing I notice is that Y, this length PR, is actually the diameter of my circle. So to find Y, I can find the radius here, QR, and then multiply it by 2 to get PR. And what's really important for me here is that I know from theorem 10.9 that if my line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. In other words, we have a right angle right there. And one thing to point out before we go any further is that because even though RS is a segment can still be tangent. Because this line is tangent, technically we usually talk about tangent lines, but a segment is just part of a line. So this tangent segment is just part of what a whole line that we know would be tangent there. But you can have tangent lines, tangent segments, and tangent rays. So if this is a right angle based on my theorem 10.9, perpendicular at my point of tangency, I know I have a right angle, and of course if I have a right angle, then this is a right triangle, and so I can use Pythagorean theorem to solve for the one missing side. And of course when we use our Pythagorean theorem, it's going to be 16 squared, and again forgive my writing as I get used to this thing, plus I'm going to say b squared is equal to 20 squared. So, and remember, of course, In the Pythagorean theorem, the hypotenuse has got to be sort of what we would normally call c squared, or the one that's by itself. So then when we solve this, 16 squared, I believe, is 256. If we want, we can grab a calculator here real quick and check that. So let's just grab my calculator and bring it down here. I'm going to do 16 squared equals 256. So that was fun. So 256 plus b squared is equal to 20 squared, which is definitely 400. Subtract the 256 from both sides. And then b squared is 400 minus 256, which should be 144. And so my last step here will then, of course, be to square root both sides, because I don't want b squared, I want b. So we take the square root, and then b, oops, I grabbed the wrong purple, but that's okay, should equal the square root of 120 or 144, which is 12. Now b, remember, was just half of this because I'm using the right triangle. So I need to double that to get y. So y is equal to 2 times b, which is 24. And remember, the only reason I could use this Pythagorean theorem here is because theorem 10.9 says that my tangent is perpendicular to the radius. And of course, YR is a radius here. Okay. So that's one part of section 10.5. Let's look at one more theorem from 10.5. So here we have theorem 10.11. It says if two segments from the same exterior point are tangent to the circle, then they are congruent. So here we have a great example of this in what's number 16 from the book. It says we have DE and DF, and they are tangent. The directions in the book say that anything that looks tangent is tangent. So I'm going to say that DE is tangent, and so is DF. Now this theorem says two segments from the same exterior point are if two segments from the same exterior point are tangent to the circle, then they are congruent. So because my two tangents come from the same exterior point, D, I know that they have to be congruent. So then very simply, if I'm going to find x here, x minus 2, the length of my one tangent must be equal to 14, the length of the other tangent from the same exterior point, and we solve. And of course, x is 16 when I add 2 to both sides. Good. Now let's jump over to 18 and look at one that looks a little bit more complicated, and maybe it's a tiny bit more complicated, but not too much. Now we're just trying to find x here, but let's go around and fill in some things that we know. Here I see several places where I see a tangent coming from the same point. So I see that this little segment here is 8. So then this little segment should be congruent to that and should also be 8. Ooh, that was a good 8. Up here I see this PW and PQ are both tangent, and since they share this exterior point P, then this little segment here should be 3. Good. And if we keep going around, I can see that this little piece here, UT and TS, should be congruent because they're also tangent. They're both tangent, UT and TS, and they both come from the same exterior point, T. So this length here, which I'm going to kind of highlight here in purple, that length should be 4. I'm going to grab a different color here. And I see up here QR and RS, those are tangent and they have the same point in common, R, the same exterior point. So this length RS that should be equal or congruent to this other tangent RQ that comes from the same point. So that should be 6. And now I'm trying to find x, so if RS is 6 and ST is 4, then x is 10. The 6 and the 4 together. And so those are the two theorems that we use with tangents. Theorem 10.11, which says that if two segments from the same exterior point are tangent to the circle, then they are congruent, and we use that in these two examples. And then on the other page, if a tangent is, if you draw a radius to the point of tangency, then that will be perpendicular to the tangent line. So we can use that as well. So these are the theorems and definitions that we need from section 10.5, as well as some examples that might help you in your homework. Okay, enjoy section 10.5 and learning about tangents.